Okay, good morning and welcome to what I think is lesson 14. The topic is parametric unit hydrographs, which will complete our introduction to unit hydrographs per se, and then synthesis. Parametric unit hydrograph replaces the discrete unit weights that we computed last time with a functional representation of the unit hydrograph. So in some sense, there's no difference whatsoever. But on another much bigger sense, there's a huge compaction of information in that the functional form and whatever handful of parameters are associated with that function are the unit hydrograph, and the individual weights are computed as needed. The big advantage of that is that we only have to keep track of the function name and the various parametric components of that function. And we'll motivate that by an example. So this figure here on your screen, which I pulled up so that when I render the videos, this can become the, what is called, the thumbnail sketch, or the clickbait, depending on your context, illustrates this rather convoluted process, pun intended, on how things proceed. So imagine, if you will, we have an well, we got more people coming in. I need to have this thing tell me when people show up. There we go. Okay, welcome everybody. And I was babbling aimlessly until you all arrived, so you haven't missed anything huge. The topic for today are parametric unit hydrographs and hydrograph synthesis. So a parametric unit hydrograph replaces the discrete weights with a function. And if I can escape from this presentation, there we go. Oh, that was seriously escaped. Let me bring back our prior lesson. So our discrete unit hydrograph was aimed at finding this vector of weights, and these had numerical values: 436, 912, and so on, 403, 10, 79, and so on. So these weights, when pre-multiplied by the precipitation matrix, produces our response matrix. The difficulty in these weights is that if the hydrograph gets longer, we have to extend portions of the weight function, and so to represent, in this instance, 24 time units, this weight vector here has 24 elements in it. So imagine if we wanted to do 1 minute responses for one day. That's 1,440 minutes, or in a day, you'd have 1,440 weights. 2 days, 2,880. 10 days, 14,000 weights. Still within the realm of modern computing, but now we're starting to get into a great number of opportunities for mistakes to creep in. So the parametric unit hydrograph concept replaces those weights with a function, a decaying exponential usually. And in that function, all we record are a couple of parameters, perhaps a scaling parameter, a time averaging parameter, and a shape parameter. 3 numbers instead of 14,000, and we can represent the functional form in that fashion. So that's what the topic for today is. And that will conclude what I think is the necessary background for unit hydrographs, and we'll start applying these in our analysis software. So, nowadays, I don't think the construction of a weight vector is as common as it used to be. And let's see, I already have that up and live. Lesson 14. PowerPoint. There we go. So I will actually I want to return to this picture. So let's return to this picture and kind of briefly refresh our minds on what's going on. Here's a precipitation signal, a hydrograph with different pulses of precip height in time. That's fed into some kind of loss model. And what comes out of the loss model you can think of as having the same shape as this thing, but the heights are a little bit lower to reflect that losses. The result of that loss model, it goes right here in this forcing function, x of tau. There's a unit hydrograph model, which is called the unit hydrograph kernel, and that's represented by this function, h of t minus tau. And the tau is the time shift. It tells which of the weights you use with respect to which of the forcing impulses are being considered at some moment in time. If we perform the integral from minus infinity to infinity of the product x of tau, h of t minus tau, we get the result that's called the convolution integral. And one mathematical representation to write it is x of t, and this isn't the ordinary multiplicative operator, it's called the convolution operator, h of t. What comes out of that is the response function, the discharge. So precipitation goes through loss, goes through the convolution integral, produces this discharge signal. And we're going to examine the unit hydrograph kernel. So the readings are pretty much the same ones as before. The difference between analysis and synthesis are shown here in these bullet items. If we're doing analysis, it means we have observations, and we want to create a unit hydrograph for later use. So we'll focus on that first today. Then we'll get on to synthesis. In synthesis, you don't have observations. We want to create a unit hydrograph for later use, and what we do have are a description of the watershed. So we know its area, main channel lengths, slopes, soil coverage properties, things like that. What we don't have are paired rainfall runoff observations, and that's usually the case. The whole point of doing, one of the main points of doing hydrology and rainfall runoff analysis and synthesis is to predict things on ungauged watersheds. And so those predictions are based on correlations between gauged watersheds and their various watershed properties. So parametric unit hydrographs, a lot of words here. I will read them, and with any luck they'll make some sense. So parametric unit hydrograph are simply functions with parameters. As an example, consider force equals mass times acceleration. The parameters of that are mass and the acceleration of the object that produces the result of force. If we have the parameters of the hydrograph, we can reconstruct it using the function rather than keeping around that vector of response values. Using that 10-day example, that 14,000 plus length vector. So we're going to go through an example, and the transfer function I'm going to use is that the unit weight as some function of time is equal to k multiplied by the elapsed time divided by some timing parameter raised to the power n times e to the minus time over some timing parameter. So I've created that function. As far as you all know, I just pulled it out of the air. The particular structure there happens to be a gamma distribution, and those have been shown over the years to be pretty good representations of watershed response. But that's sort of irrelevant. Consider I pulled this function out of the air. Now, it wasn't completely out of the air because I picked a function that I know has kind of the right shapes. So the unknown parameters we have are k, capital N, and t. And in terms of associating with common names, t is a timing parameter and it locates the peak of the discharge. It's conceptually analogous to a time to peak or a time of concentration or a basin lag time, depending on how we fabricate that equation. In my writings in the past, I call it a characteristic time. The parameter k is related to the drainage area, and n is related to drainage shape. But like the timing, they're not easy to infer from maps. So the main difference here between the prior lessons is that the unit weights are simply values of the transfer function at different locations in time. So instead of keeping 9 unit weights or 1400 or 14,000, we only need to keep the 3 parameters k, n, and t. It has another particular advantage is extending the time base becomes almost trivial now. So going from a 9 time unit information structure to 14 to 24 to 200 is simple because nothing changes. All it is that we're calculating these unit weights further out in time based on this function. So to estimate k, n, and t in the case where we have observations in the analysis context, we're simply going to construct the same linear system as before, q equals p times u, where u is given by the function at the correct times. Then we adjust the values of k, n, and t to minimize the difference between the observed discharges and the model discharges. And on the next figure 17, which should be appearing in the next slide or two, is an example of this done in Excel. And the merit function that was used in the example is the sum of squared differences at the peak, but there's others that can be used. So the process of using a minimization procedure to estimate the parameters is called deconvolution. And it's a big deal in information science. It's somewhat big deal in hydrology, although historically in hydrology we've not routinely associated the problem being the same problem as getting a cell phone to decipher a signal from millions of signals. But functionally that's the same problem. And so here's the problem displayed in a spreadsheet. I have cats in the background that are deconvolving each other's fur. I'm going to let them play for a while. So this is the same hydrograph information as we had earlier. So there's the time signal, 1/2 hour, 1 hour, 1.5. The increment is just a counting feature, and the excess precipitation and the direct runoff. But now instead of using the linear equation solver to find this purple vector, we have this function up here that has a parameter of k, n, and t. And by changing these numbers, it changes the contents of this purple vector, and the precipitation vector multiplied by the purple vector produces the model response, which is this vector here that the cursor is cursing on. And then we take the difference between that value and the true value over here, 428. Store all those differences, square them, and that becomes the bias, compute an average bias, and then try to minimize this number right here. And in this particular picture, this looks like this is the solution. So this is the functional representation that produces this red curve, whereas the black dashed curve is the observation. And even though there's substantial bias, which will always be the case, that's not a bad representation of the unit, of the hydrograph response. Now where it comes handy is when we're going to apply a different rainstorm. Here's the same problem done in our script, which I checked on earlier, and that's located on the server, and I will show you where, only if I click on the correct deal. So that is the function that will produce this response. So that is shown right here, and we can test that shortly in the shared hydro environment, but we're going to proceed forward a couple more slides before we do that. So Excel's good for teaching yourself what's going on, but for real hydrographs, and I'll show you why, it becomes essentially useless because of the size of data. Not hopelessly useless, but not the best way to do it. Here's an R script, which is somewhat better than Excel when the problem gets big, doing about the same thing. And here's the value of the parametric unit hydrograph. There's actually a fourth value here that I'll state out loud when we get to it. There's fewer things to keep track of. That's one of its benefits. Extending the time base, so making it deal with longer and longer inputs or response time, is very simple. When we can associate those parameters, the K, the T bar, N, and so forth, to watershed metrics such as the slope, the main channel length, soil properties, some shape of the watershed, whether it's fan-shaped or long, slender, the resulting model is called the synthetic unit hydrograph. So when you see the word synthetic unit hydrograph, all that means, it's jargon for, I have a unit hydrograph function, and I have a way of associating the slope, the area of the watershed with numerical values of those parameters. It's called synthetic because the response is synthesized from metrics rather than observations. And we may not have observations in cases of practical interest. So here's an example of extending the time base. In this example of extending the time base, all that was done was the designer simply added rows to the worksheet, structured the precipitation matrix correctly, so it's more than just adding rows. They had to add the right rows and columns, and then literally did a drag and drop of this vector here and these carry along vectors. That was the only change, so just made it longer. And that's a substantial reduction in effort as compared to keeping track of unit weights. Then they can apply a different storm, as is done here. At that point, with a different storm, we don't actually have any real runoff to compare to. So the calibration one is just stayed in the plot. it has no particular value here. And we will conclude, and then we'll go to the R script and look at some features of that. So unit hydrograph response is usually expressed in this equation here. So in this case, it has Q of T divided by the area, where Q is the observed discharge from a basin at the pour point in time T. Call that the response. A is the watershed area. A is simply a scaling term because we're taking rainfall input as inches of depth. It's convenient for analysis and for synthesis to have our response also be in inches of depth. So the area is what converts between cubic feet per second, if you will, and watershed inches per second. So the input function is R, the rainfall, and here it's subscripted with excess to remind you that it's excess rainfall. And then U is the kernel function. And it's called a kernel because this particular mathematical operation is integrating a kernel and a forcing function, and it's called convolution. So equation 4 is assuming that basins behave as linear systems, and that assumption is a legitimate criticism of unit hydrographs as a theory for explaining watershed behavior. Despite that criticism, they've been used to estimate stream flow from small basins to actually pretty large and produce reasonable results. And an explanation for that is a watershed is a natural integrator of all the processes, and whatever nonlinearities it starts out with, because of the scales involved, the behavior is somewhat linearized by the various processes all competing with each other. So that's a hand-wavy explanation. Probably the simple one is it's worked pretty good for 200 years. Why stop now? With the linearity assumption, the kernel, that U of T minus tau, has the same properties as probability density function. Specifically, it'll integrate to unity between minus infinity and infinity, and it's always greater than 0 for any values of times greater than 0. So it has properties of a probability density function that are defined from 0 to plus infinity. We can use that advantage in picking functional forms of the unit hydrograph. So if it has to behave like a probability density function, let's just pick probability density functions. And some of the ones that have been successfully used in the past are gamma distributions, which is what I used to create that earlier example function. Log normal's not bad. Log Pearson type 3, which is the same as our flood frequency analysis tools, is not bad. And there's a host of other density functions available. Naturally, one would want to choose the function that has the fewest parameters that can still produce the shapes that we desire. Okay, so let's go ahead and visit these examples here online. And with any luck, I think I did it here in the development environment, but if not, we'll find out in a second. Yeah, it looks like I was over here, so that's good. And it looks like I have not downloaded the file, so let's go ahead and let me go ahead and change the name of this one slightly. No, never mind, I'm going to leave it be. My internet's kind of going slow today. All right, let me grab parametric response. And actually, I need to get all these files. Save link. Yes. Okay. So these illustrative examples are just that. They're to illustrate what's going on. Under many circumstances, it'd be better choice to do the analysis in HEC HMS or SWIM. But here we're going to show it using our R scripting tool because we have to understand the arithmetic going on underneath it. So let me open the parametric response model. Should be set to go in RStudio. Kill this guy. Kill that one. Set directory to the source files, and then we're going to first take a little look at the code involved, and then we will run the script and hope it works. Okay, so here we have parametric model convolution, blah, blah, blah. So it's taking as input precipitation, the kernel function, and the kernel function structure. So that's going to be K quantity T over cap T raised to the power n exp to the minus T over cap T. Here's some prototype functions that are there simply to decipher the input time series. So it's these exist in case the input are in cumulative fashion. And then here's the kernel function. So it's called unit for lack of better name, but it could have just as well been named kernel. The main problem with naming kernel is used in other parts of the R script, so naming it kernel's fundamentally kind of a stupid move. So I've called it unit. And let's see what unit accepts as input. It needs a scale parameter, a shape parameter, a resonance time parameter, and something about time. And what it returns is it takes the scale, it multiplies by minutes over resonance time raised to the shape, times the E function to minus minutes over resonance time. So that's not a terribly elaborate function, but it's going to have all the properties of a unit hydrograph. If you were to integrate that for any value of scale, shape, and resonance time that are non-zero, from minus infinity to infinity with respect to time, it would integrate to 1. Well, actually, that's a lie. You would integrate it, and you would adjust scale until it integrates to 1, and then you're happy. Here's the convolution function that performs the convolution integral for us in discrete space. So we have this response vector. We populate it based on how big it needs to be. So we have to tell it the size ahead of time, and then it performs the convolution arithmetic for us based on that size. So it runs tau, which is the I index, from 1 to n1, and it runs t, which is the j index, from 1 to n1, and in the kernel is where the time shift occurs. So it's time minus tau. And then we take the any value of response that was there, and we add it to the computed convolution in the sign vector response. So that's our convolver. And the next part actually performs the analysis for us. I'm going to modify this in a second. So we're going to read from a file, and it says, let's see, rr1m example.txt. So we'll take a look at what that looks like. And once it has that, it gets an average rainfall rate and an average flow rate. So it's doing this backward rate, backward time, which means the data in this file are provided as cumulative. Produces an excess by proportioning it so that the two volumes add up correctly. So you can think of this is called a proportional loss model. So if the total runoff time series adds up to, say, 7 watershed inches, and the total input time series is 14 watershed inches, then the excess is 0.5 times the input. And that's how this functions. So what I'm going to do is I'm going to copy these. And code. We'll start with the answer, and then we'll revisit. I'll change some values here. What I normally would do is just start with some guessed values to get an initial guess, because we don't know what the correct values are when we start. But we'll start with these as is. So it has a scale parameter of 32, shape of 5, resonance time of 0.3, and none of those are in humanly interpretable units. So it uses the current value of scale, and it integrates the unit hydrograph. And then it adjusts the value of scale so that the unit hydrograph sums up to 1. So for long time series, this is a pretty useful activity. For short time series, for 15, it's kind of a hack. Then we're going to check that it sums to 1. And then we actually compute the unit responses. So the unit response vector is the unit function evaluated at all the minutes of interest. And then we compute the model flow rate by convolving the excess rainfall rate and the unit response. And then finally we plot everything. So I'm going to run this once. Hopefully it will work. Save the changes and pray. As usual, oh, that was intentional, actually. I laid behind a okay, so it can't detach what's not there yet. So we just read the data. Oh, we should go take a look at the data first. So here's the input file. Minutes, cumulative rain, cumulative runoff. And these look like it's the same information as the example problem from Chow Maven and Maze that we've been using. So now we'll return to the program. Let's see, we'll attach the headers, compute the average rainfall rate, average flow rate, excess rainfall rate. So now we will compute scale, and we will verify that we get a 1 back, which we do. Unit response has been computed. Model flow rate's been computed. And now we will plot first the excess rainfall rate. So here's our rainfall excess. So the first one is at 0.5 and then at 1. Let me modify the plot type. So here's our 2 excess values, and there must be a 0 here at 0.5. Then we're going to put our average flow rate, which is the observed flow rate. So these are our observations. There's the observed, and then here's our convolved signal. So not perfect, but reasonably close. Now let's play the game where we don't really know what the scale is. And we'll pretend that we're lazy analysts. And so we'll pick a scale of 1. And we've read Lienhardt's paper, and so shape parameters much bigger than 3 don't make sense. And we'll assume our residence time is 70 time units. Okay, so there's no way the pictures are going to look the same. Okay, so that's, if we look at our computed hydrograph, it's not a very good representation of the observations, so we need to change something. So let's change the shape to 6, and we'll rerun all this content. Well, that didn't help us, it made it pointier. So because the peak is way off to the right of the observed one, our residence time seems to be too big. Let's reduce it by a factor of 10, and we'll reanalyze. That didn't appear to do very much for us. We'll go to 1. Okay, so now we have the peak here and the peak here, or at least in the same picture. And our computed hydrograph is too flat. So we'll increase the scale factor. And so I'm just kind of doing this willy-nilly, and then we'll suggest a more systematic way. And that had almost no impact with us. Let's try to get that peak closer to this peak and this peak closer to each other. So in terms of systematic fitting hydrograph by trial and error, the first component to fit is the timing. Once the timing has been established, it's usually pretty straightforward to tidy up the rest of the hydrograph. So 0.5 wasn't very good. We'll go to 0.25. And run that. My doorbell just rang. Take a 1-minute break. I'm going to go see what that was. Alrighty. Nothing important. And so now we've got the residence time pretty good, and we can try to work on getting a better fit of the shape. That had almost no impact. Okay, so at this point, we're now dealing with very small changes in behavior. Let's see what we can get right here. I'm going to stop on this one. Okay, so we are getting changes. So from here on, you'd make very small changes, and visually, there's not much you can tell. At that point, we'd have to go ahead and introduce computations to calculate the error between the red curve and the black curve and refine upon that. So let me go back to the correct values. 31.9 should be close enough. 5.7, oh, I'm going to call that 5.8 should be close enough, and 0.3. We'll declare that our unit graph. So there's our unit hydrograph, if you will, after our trial and error fitting process, and we would conclude that no further changes of these numbers provide much benefit. So our unit hydrograph would then be expressed as that function using these values. 4 pieces of information instead of 24. Now, where the value of the utility of this comes is not in these small problems, but when we get more interesting problems. So let's take a look at real file. So here's one for, God, this weird layout. I hope I can read that. That extra line is confusing to me. So here's one for the Ash Creek watershed, and it has 2,879 entries in it. That's conceivable in a spreadsheet, but take you 2 minutes just to scroll down through the thing. This is one where we'll want to use the ability to process directly. So I'm going to use the same model, and I hope I got the file names correct. Let's save that. And so nothing else changes. I think I can start from here. So now I've read the new data in, same set of things as before, and there's no way those are the right numbers. We'll have to figure out how to fit it. Okay, so now in theory we've just passed all our information through unit hydrograph. There's our rainfall. I'm going to switch it back to a different plot style. So there's rainfall in magenta. Excuse me, excess rain in magenta. Here is our observed flow rate from that gauge in black. And here will be our model flow rate. It'll be in red. Now we're just using numbers that were left over from our last analysis. So I have no expectation for them to be at all close. What I'm hoping for is that at least the peaks are in the same plot, because then we can adjust it and well, that's peaks are all in the same plot. So that one is as if there is no transformation. We can see that the runoff is almost exactly following the rainfall input in our model. So we actually need our resonance time to get bigger. I'm going to use some prior, ooh, I don't want that to happen. Is there an undo? Yay. I'm going to use some prior knowledge. I know that the resonance time for a gamma distribution for this particular watershed is somewhere around 70 minutes. So I'm going to put in 60. and see what happens. So what I'm expecting is the red peaks will shift to the right. Hit a save, and we'll rerun everything there. Okay, they shifted to the right as expected. They actually dramatically changed shape. So I'm going to reduce my shape to a 3. See what happens there. And I think my scale needs to be bigger. And like before, I'm really pretty much trial and erroring now. And with a little bit of additional work, I need to make the hydrograph itself skinnier, so we can ask myself if making the shape large helps, and then the scale will be the last thing that I mess with. Okay, so that's the wrong direction for shape. Let's go to a little bit less than 1. All right, I like that. And then residence time, we'll go back up to the 70 minutes that I think it should be. And I'll stop after this one because I just broke it. So, all right, that's incomplete, but you get the idea. Okay, so one of the obvious observations is doing this by trial and error is ultimately hopeless. And if I were smart, I would have left notes to myself on what the residence time should be. 35.5. That's the best I can do while doing this on video. All right, so that is the use of the parametric unit hydrograph. Let's say, for the sake of argument, let's say that that was the best fit we could get. Then we could report the unit hydrograph for the Ash Creek watershed is this function using these 3 parameters. And then we can apply that to future or other rainfall time series and use it to predict the response. So that's the essence of a parametric unit hydrograph. So there is another way to fit hydrographs, which is the last one, which is the optimization approach. And I have a cat's tail in my face. I have a script of that already built. It's somewhat crude because it's experimental, but it will illustrate the ideas. So I'm going to kill these off. So all this stuff that I just did is in the file server for this lesson. Open, optimization. it works on a file called example1, comma save value. So let's go look at that file. And this is again the example of chow mein and maize. So I'm going to clear all these plots. And we'll resume that one. So this is going to read the file. Well, we'll just run through it one line at a time, and I'll comment as we go. The tricky part is down in here. So it's going to read the file. Well, I guess I should run the whole thing once to be sure it actually works. This is a very complicated structure right down there. I think I can put a line feed right there. And I can put a line feed right here. There we go. I don't know why it was written like that. So here we're going to read the file. We're going to attach the headers. We're going to list the contents. So we've read the file. I believe that's correct. When we get the length of those vectors, we're going to create a space for discharge. We look up here, there's a bunch of zeros right now. We're going to create a space for unit responses, which are also, there are a bunch of ones right now. And then we're going to set up some plotting stuff. So first we'll plot the hours versus the excess rain there. Hours versus direct runoff there. And we've created an error vector, which is the direct runoff minus the discharge. And if we look at the current error vector, because our current computed discharge is zeros, it simply returns back the input. So the error is quite large. And so now we have a model which is a function of excess rain and unit response. And it's going to produce, this is doing the convolver here. Let me introduce some line feeds so it's easier to read. I hope I'm not breaking it, but we'll know in a minute, won't we? There we go. Okay, so it takes the value of discharge. It looks like it sets everything to 0 all over again. And then for going from 1 to however many elements there are, and then it goes from j, starting from whatever the value of I is, to however many elements there are. It simply performs a convolution and then returns the result. Now we will take the Q model we just computed. We will subtract the direct runoff from it, and we'll square that result, and we'll call that the error function. So here's the error function that essentially does this, the sum of squared errors. So now we need to run that function. And now we're going to use a tool that's built into R called nonlinear optimization, NLM. And what the nonlinear optimization needs is a function that computes the objective value, in our case error, a function that contains the inputs, in our case the unit weights, how big everything is, N1, and then any additional terms that are needed for the error function to operate, in this case excess rain and direct runoff. And the NLM will attempt to minimize the error by changing the contents of this vector right here. And when it gets done, it will return a unit response vector and a value of the error vector. So this one line is doing a whole lot. So we've just minimized the error. Now we will compute the discharge. The red circles we just plotted are the computed discharge from the minimization. You can see rather remarkable fit, and then we will find it and write the three results. The only thing it did wrong is it has the unit response vector wrong. So we will make a quick code modification right now. And we actually want to plot the unit weights, which is y estimate. I think that's correct. So here are our unit weights computed by optimization. And here's our error vector, the last column. You can see that it's really pretty good. It's a fairly straightforward modification of this script here to do the same thing for the Ash Creek data that we've already done. And it does not look like I have an example of that pre-built. And in the time remaining, it would be a foolish use of the video to try to do that before your very eyes. So for the time being, I'll say you have to take it on faith. It's relatively simple to convert this to operate on the Ash Creek data and use nonlinear modeling to compute the required values of the parameters to satisfy the analysis for the Ash Creek watershed. So let me return back to the PowerPoint presentation and prepare you for tomorrow. So what we'll do tomorrow is we're going to look at everything we've just done, but using the HEC-HMS. So we've done analysis, we haven't really done synthesis. The idea of synthesis is we're going to use physical properties of watershed to postulate the transfer function. Actual measurements are not required, so it produces an estimate. Some examples of the parametric unit hydrographs that are built into the computer programs. In HEC-HMS, there's the NRCS dimensionless unit hydrograph, Clark unit hydrograph, I think there's Snyder, there's a few other ones, and they get named after people. All they really are probability density functions with one or more parameters. And then the parameters have been associated with physical properties of the watershed by the various authors, and the ones that survived into the software are the ones that have worked well throughout the world. The selection of the parameters selects the shape of the unit hydrograph, the time base, and the time when the peak occurs. We can also enter an empirical unit hydrograph. So the ones we've been building, based on those unit weight values, those are empirical hydrographs. And there's an ability to supply those directly to HEC-HMS or SWIM. So to develop it by analysis, you can follow the FHWA methods, which is essentially back substitution or ordinary least squares, which we've already examined. We actually have R scripts to do that. You can use Heck HMS or SWIM in a parametric unit hydrograph and actually adjust values to fit the observed runoff. In my opinion, that's less tedious than the first bullet item. You could also use a user-supplied unit hydrographs and adjust values of the ordnance to fit observed runoff. So the second two bullet items there are a rather cleverly disguised optimization approach. So we'll go ahead and we'll assume the unit hydrograph function to begin with, and we'll simply turn knobs on it until it fits the observed runoff. And then presumably we'll have one other observation set to see how faithful that is to different conditions. So we're going to use an example starting tomorrow where we'll look at the NRCS and the Clark unit hydrograph. They're selected because they have the fewest parameters. NRCS, all we have to provide it is a timing parameter. The Clark has a timing parameter and what they call storage delay factor. Snyder is also a 2-parameter hydrograph. Gamma is also a 2-parameter hydrograph. Other ones have more parameters. Once we get more parameters, it almost becomes hopeless doing it by trial and error. It's still within the realm of optimization. You get too many parameters, and we're forced to do it all entirely computationally. Synthesis generally doesn't use data. It uses measurements on the watershed to postulate parameters of the unit hydrograph. And so what we will do, I'll go through the rest of the slideshow today, but we're going to do this example that's illustrated here. We'll learn how to use HMS to build a parametric unit hydrograph. We'll use trial and error using observations, and then we'll learn how to supply an arbitrary unit hydrograph to HMS. We're going to use example 6.2 out of highway hydrology, which is one of the readings. And the watershed that we're going to have has these known properties. 0.39 square miles, unknown slope, unknown curve number, precipitation, direct runoff are given. So it's this example out of the book. CU means conventional units, or U.S. customary, if you will. We do know the slope, actually, so that's a lie right there in my bullet item. And this part here is a volume balance, which is of some consequence for doing this by hand. So we would prepare the precipitation for that example. So this is a precipitation spreadsheet. Direct runoff has already been given. And then the approach would be to create a single basin watershed, import the rainfall and runoff, adjust losses in unit hydrograph models to fit observations, interpret, and report the results. So here we go from scratch. You can see that this is an older version of Heck HMS, so when we do it tomorrow, things might be slightly different. So we would create a new project. We would create a basin model. We would create a meteorological model. Here be sure to include the subbasins. Here we supply the specified hydrograph, and here it's starting 1 January to 2 January. We would insert the discharge gauges so that we have a way to compare output. But notice it has a lot of error messages because we have a lot of zeros. And it's in our benefit to go and repair those. Then we go to the sub-basin. We're going to give it an initial and constant loss and an SCS unit hydrograph. Lag time of 30 minutes. And now we're going to go ahead and try to deal with the missing data. So we've now repaired that and run the model. And given that there's no losses shown here, the initial constant values were set that there's no loss. But now we have the response, and the black dots are the observed values, and the blue one is the computed hydrograph. And we see that in our computed hydrograph, there's 0.3 of an inch of total runoff compared to 0.16 inch observed runoff. So we need to make some changes in the computed hydrograph. So in this case, we're going to incur an initial loss. And that's it. We're going to take the first 6/100ths of an inch off the rainfall time series and then reapply it. And when we do that, we can see that we're now getting closer. We'll make another change. In this case, we'll put the constant loss rate of 0.16 inches and then rerun the simulation. And here we have the loss and then the excess. And now we have a pretty decent fit of the peaks. And in fact, our main error occurs right there. Our total runoff is 0.16 inch. Our observed runoff is 0.16 inch. We've matched the volumes. We've actually matched the peak discharge values quite well. At this point, we would conclude that that is the unit hydrograph for this watershed. It has one parameter, a lag time of 45.3 minutes, and a loss model of, where is it, right there, of 0.06 initial inches and then 0.16 constant rate. We could try a different loss model. The easiest from a user's perspective is the NRCS curve number model, because it only has one parameter, the curve number. So here we're providing the curve number of 98. We rerun it, and we actually have, there's a 98. Not a bad fit. Or we could apply the Clark unit hydrograph and run that, and also not a bad fit. So the last thing we could choose to do is to supply a unit hydrograph model that we create. So I call that the empirical unit hydrograph. That has to be prepared externally to the program. And then we're going to use the paired data manager to import that into the computer program. Then we run it once to guarantee that it's normalized, and then run it again on our actual case. So there's the empirical unit hydrograph, our original loss model, and that's a good fit. And now how to check that we have unit hydrographs. We can add a design storm that has a total excess of 1 unit and verify that we get 1 unit of runoff. So here's a artificial design storm that has 1 unit of precipitation. We call it pattern 1. We turn off the loss model, simply turn those terms to 0, run it, and our total direct runoff computed is 0.97 inches, which is reasonably close to the 1 inch we expect. We can rescale it once. So we take the values that were in that empirical hydrograph and divide by 0.97. When we run it again, we get 1 inch. We now have an exact empirical unit hydrograph model. And then we can apply it to our observation set. When we do that, we need to change back to the original rainfall to see that the computed hydrograph and the observed hydrograph are about the same. So to conclude, the empirical unit hydrograph and the parametric unit hydrograph, they're both unit hydrographs. The parametric has great flexibility for changing time bases. It's easier to communicate to other analysts. We only need to provide the parameter set and not a paired series of unit weights. That second feature is by far the most valuable part of parametric unit hydrograph. is we're compacting the entire response into just a handful of parameters. And yeah, those are the HEC-HMS. And if we wanted to use the gamma unit hydrograph in HEC-HMS, the example shows how we could do that. Gamma unit hydrograph is not built into HEC-HMS. Gamma unit hydrograph is by far the theoretical underpinning of most of these other ones. So having the ability to enter it directly is useful. And tomorrow we'll actually run through that HEC-HMS example. There's a copy of it up on the server in the zip file. And in lesson materials, data, so this zip file is exactly that example that I just went through in the PowerPoint. And I want to make sure that I'm giving you correct information. Wait for it. Yeah, so that's exactly the example that's in the PowerPoint. We'll work through it tomorrow because that's a useful exercise, and that will complete all the pieces that are needed to use either HEC-HMS or SWIM as a hydrograph modeling tool, as a watershed modeling tool. And then we will examine some more materials related to routing hydrographs from one point to another. And by the end of the week, you should have pretty good background in anything you could need to do to model a watershed. So that concludes today's meeting. And I'll end the meeting. If there's questions, now's a good time to ask them because it's about to end. Okay, that was very antagonistic. Does anyone have any questions? Okay, well good. I'll see you tomorrow, same time. I will update the Moodle server because I assume I didn't get to that Friday. Some curriculum stuff came up. It won't affect any of you all directly. You'll be graduated by the time the changes are completed. But we're under a corporate gun to get it done kind of in a hurry. So you all know how that goes. When the bosses tell you to do something, you go, how far and which way? Okay, well have a great afternoon, and another Monday has come and gone. Felt like a Monday for me. And I look forward to continuing tomorrow. And I will produce an exercise set for this week. I will endeavor to get it out sooner rather than later. It's going to comprise work on the Ash Creek watershed. I'll have the data as prepared as possible. And that's it. Have a great afternoon. Bye-bye.